Thank you for the introduction. And my name is Jiabin, and actually I'm not the author of this paper, and I'm a presenter for this paper from the University of Hong Kong and also Baidu. And the title is GraphGPT, Graph Instruction Tuning for Large Language Models. So first of all, what is graph data? Graph data consists of nodes and edges, and that can be used to represent complex relationships between entities. And you may learn it from some discrete mathematics, and this type of data has extensive applications in many fields, such as social network analysis, drug discovery, urban computing, and so on. And recently, we can see that the graph neural networks have been proposed to model graph data using deep neural network techniques, result in significant achievement. However, unlike in image pixels that have a uniform RGB representation, the semantic relationships in different graph data vary greatly, making it impossible to model with single graph neural networks. And meanwhile, we can also see that those large language models like ChatGPT, which are trained on vast data and utilize an increased number of model parameters, have achieved astonishing and exceptional results in many areas of natural language processing and also information retrieval. And particularly noteworthy is their impressive transferability and also generality, which enables them to handle tasks they have never been trained on. So the motivation of this paper is to let large language models understand graphs and directly do downstream graph tasks, for example, like node classification and link prediction. But however, effectively combining LLM and graph learning as a predictor poses non-trivial challenges. The first challenge is how we can feed graph structures into LLMs in natural language or other forms. And the second research question is how we can empower LLMs to understand graph structure. That is how to align the LLM's ability with graph understanding. And finally, how to endow LLMs with the capability to reason step by step for zero-shot complex graph learning tasks. And generally, we would like to figure out how the LLM can be used for zero-shot graph learners. That is, for example, if LLM can do the unseen graph task. And so here, the author would like to address this challenge one by one. For the first research question, there are mainly three approaches in the current literature. The first one is that for specific paper classification in a citation graph, we can actually just use those kind of paper tags, so which means that we can just classify the paper without the actual graph structure, which means that we will not provide those kind of neighborhood information. But we found this kind of approach may fail even using the ChatGPT when the paper is like in some interdisciplinary field, which means that its neighborhood information will be very important in terms of those graph tasks. And another method is to actually feed a text-based graph into LLM. The text describes the connection information in the prompt. However, it still seems that they cannot adjust the error, and also it makes the token length too long. And as we all know that the input context length for LLM is actually limited. And the last case is the result generated by the graph LLM proposed in this paper. And only with 7 billion parameters, we can see that the model can effectively input the graph and let LLM learn from the graph structure, and also the input token length is actually controllable in the proposed graph GPT. And then let's introduce how they achieve this kind of approach. First, they introduce the graph token, and they regard the graph as a sequence of graph tokens, and the overall architecture is shown in this figure. The graph is first encoded by a pre-trained graph encoder, and the graph encoder here could be any graph neural network. And the graph embeddings are then fed into the projector to obtain the graph tokens. And then we can put the graph tokens and natural language tokens together to let the LLM understand the graph and follow the instruction to do the downstream task. And in particular, with the first part of the GraphGPT is the text graph grounding. And here we initialize the graph encoder with natural language alignment. And we use the graph text pair and pre-train the graph encoder in a contrasted manner. And the second part of the graph GPT aims to address the research question 2, which is how can we empower LLMs to understand the graph structure? And the answer is that the graph instruction turning paradigm proposed in this framework, the graph instruction turning paradigm actually has 2 stages. The first stage is called self-supervised instruction turning. We input the unlabeled graph into the LLM, and that let LLM match the graph tokens with the corresponding natural language content in the prompt. For example, for different nodes represent different papers, we would like to let the LLM based on the graph tokens and reorder the shuffle paper list. Note that here we just tune the parameters of the projector, so the alignment is very lightweight, so we do not actually need to fine-tune the whole LLM, and here just need to fine-tune the projector. And then for the second stage is the task-specific instruction tuning. And here we use the instruction data about some downstream tasks, for example, like the link prediction, node classification, and this kind of downstream tasks, we formalize them as some task-specific instruction turning task. And then for the third research question, here we distill reasoning capability from a powerful model such as ChatGPT through the chain of thought prompting. And GraphGPT is, here we use ChatGPT as the teacher and GraphGPT just as like the student to distill the knowledge from the ChatGPT. And the ChatGPT is actually a very powerful but closed source and also costly model. And the proposed GraphGPT just with 7 billion parameters is very lightweight and also, but it's not that smart, so we can use this kind of chain of thought distillation to handle this kind of issue by just learning from their teacher, such as the ChatGPT. And here we come to the experimental results. And from the experimental result, we can see that the proposed graph GPT actually outperformed the state-of-the-art for not only the supervised setting, but also the some zero-shot setting. And it's worth note that here this work is first to propose to deal with the zero-shot challenge in the graph learning domain. And also, here I would like to highlight the generalization capability investigation of the graph GPT. And specifically, we mix up different kinds of instruction data to obtain multiple data combinations, such as different data source, different data pattern. That is whether contain like ChatGPT, the chain of thought prompting, and also different tasks like the node classification and link prediction. So from the result, we can have some interesting observation. And the first one is that the more data will actually boost the model transferability, which means that the significant improvement in the zero-shot setting can actually derive from this kind of more data. And the more data, but also will not result in some forgetting performance in the previous task, which means that the training process of the GraphGPT on multiple data sources is actually feasible, is a appropriate way to prevent those kind of forgetting during the continual training. And it will learn both all of the tasks of them and will not occur this kind of catastrophe forgetting. And moreover, we can also see that there is an experiment for the generalization for multitask graph learner, which means that we use the multitask instruction data, and the proposed graph GPT tend to be the multitasking graph learner, and different tasks can benefit from each other in the experimental result. And in the experiment, we also conduct some evaluation study, including the effect of graph instruction turning, and also the effect of LLM enhanced semantic reasoning. And also, we conduct some model efficiency study, including the training efficiency with graph instruction turning, and also the model inference efficiency. And we can see that actually the each module proposed in this framework has contributed to the final performance more or less. And also, we can see that actually it is a very efficient method for the graph GPT. And here are some future work for this work. The first one is towards the graph foundation models, including how to encode unified semantic information among different graphs, and also the generalization and emergent abilities within this kind of graph foundation model. And the second one is towards the data-centric graph learning, including how to alleviate catastrophic forgetting in traditional graph neural network, and also more effective data-centric workflow. And also there will be some continuous updates for the graph GPT, including some efficient training within just two 3090 GPUs with 24 gigabits the memory. And also, there are more details about the graph GPT can be found in the following link. For example, there is a project page which you can scan the QR code to access the project page. And also the paper and the code are all open source. And there are also a Hugging Face website for this demo for this paper. And so and please don't be stingy with your stars to start this project for the authors. And that's all for the this talk. And thank you for coming. And this work is mainly accomplished by Jiabin and Huang Chao.